Hello, my Gen Chem 111 lab students. This is Jolly. Hey, I was just thinking I need to give you a little bit of an introduction on this lab that's coming up. So here's a little background on it, and then you can print out the lab on the printer there in the laboratory. The Corey will know how to use it. All right. So we are going to be doing what is a mole lab today. And so, just in case that we're not all on the same page, or if you haven't covered it yet, what is a mole? Okay, a mole is a quantity. That's all it is. It's a chemist quantity that is equal to the number of things compared, and for us, it's carbon 12, and it's 12 grams of it. But I call it the chemist dozen because if I say dozen, you think 12. Well, when I say mole, you need to think 6.022 times 10 to the 23rd. So, what is a mole? 1 mole is equal to 6.022 times 10 to the 23rd, whatever you're talking about, things. So, if you had a mole of donuts, well, that is a serious amount of donuts. In fact, 6022. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That is a gigantic number. That is a gigantic number. But that's how many things, and it doesn't matter what that thing is what we call 1 mole. So a dozen is 12. A mole is 6.022 times 10 to the 23rd. And now we can apply this to any chemical compound. And the way that we're going to do our reference is on the periodic table. The atomic mass is written underneath the symbol. That is how much, and there's two interpretations. So the mass can either be one atom of it, or it can be 1 mole of it. So for instance, if you're looking at hydrogen, it should say something like 1.001. That can be interpreted as 1 atom of hydrogen weighs 1.001, and we would call that an AMU, an atomic mass unit, because there's only one of them. But if you have 6.022 times 10 to the 23rd of them, okay, so 1 mole of them should weigh 1.001 grams. But if you'll notice, the unit has to be grams per mole. So you just have to note, are you talking about one specific thing, or are you talking about a whole mole of it? So those numbers, those atomic masses at the bottom of your elements, those can either be used for individual, not very useful, or they can be used per mole, which is more useful. So for instance, water, there's 2 hydrogens, so 1.001, and there's 1 oxygen, which is 15.99. So together, it weighs 17.99. Now, if we're talking about 1 molecule, it's 17.99 AMUs. But if we're talking about 1 mole of water, it's 17.99 grams per mole. So we now have a shortcut or a way to convert between grams and moles. So lots of names for it. Molecular mass, formula mass. Okay, whatever term. Molecular mass, or we could also interchange the word weight in there. So molecular weight, formula weight, because gravity doesn't change on the Earth. So we can convert, or we can just say that the mass is also the weight. Yes, I know, physics students, you're cringing. But our gravitational constant does not change. Okay. Basically, it's the weight of all the species in a formula. Oh, okay. So for instance, ammonia would be 1 nitrogen, which is 14.01, and it would be 3 hydrogens. And you take as many sig figs off the periodic table as you need. So 14.01 should be about 17.01. And we're going to always use moles, so grams per mole. So you know that there is 17.01 grams of ammonia in every 1 mole of ammonia. And so that is your ultimate cheat sheet, the periodic table, because it will give you a way to get between grams and moles. All right. What if it's a salt? Okay, there is absolutely no difference. The terminology changes a little bit. So this isn't called a mole, or sorry, this isn't a molecule of salt. It's called a formula unit. But you would do the same thing. 1 sodium is 22.99, and 1 chlorine is 34.45. So if you add them together, it's 58.44 grams per mole. Now, this one is made of atoms, and this one is made of ions. But the concept of the mole is exactly the same way for all of them. All right, well, what if you have parentheses in your, let me see, so let's go sodium. Mm, sorry, let's not do sodium. Let's do calcium nitrate. Okay, so that's ionic, so it's made of ions, but we need to make sure that we account for the 2 in there. So there's 1 calcium, but there's 2 nitrogens, and there are 6 oxygens. So when you're doing ionic compounds, don't forget I need the entire number of ions. Okay, and so 1 calcium is 40.08. 2 nitrogens, each one of them is 14.01, and 6 oxygens is 15.99. So if you add those together, six. Okay, if I did my math right, 164.04. All right. That is how you would determine the molecular weight or the molecular mass. And it works for molecules and it also works for the ions and in ionic compounds. All right, now let's use those. Okay, so let's say that I measure out, 10 grams of sodium chloride. Okay, so literally I have measured out 10 grams of sodium chloride. Can you convert that into moles? Well, yes, I just need to determine the molecular weight or the formula weight of sodium chloride. And we just did that. And that is 58.44 grams of sodium chloride in every 1 mole of sodium chloride. Grams of sodium chloride are gone. And we have 0.171 moles of sodium chloride. Well, what about water? Let's say we have 10 grams of water. If you add this up, and we just did that a minute ago, 17.99. A lot of times we just round out to 18, by the way. 17.99 grams of water in 1 mole of water is equal to 0.555. All right, so that's how you would get out of a mass and into a mole. Now, what if we don't want to stop at moles? What if we want to get smaller? If I have 0.555 moles of water, can you tell me how many atoms? Because remember, a mole will first go down to a molecule, and then it will go down to an atom. So you have a whole bunch of molecules in a mole, and then you can break it down into atoms. So I know that in 1 mole of water, there is 6.022 times 10 to the 23rd molecules of water, right? Now, whoa, that is a big number. Well, yes, because 1 mole of water has a whole bunch of molecules. Now, this won't be quite one, but there's going to be a whole bunch of molecules of water. So 6.022 to the 23rd is 3.3 times 10 to the 23rd molecules of water. But I don't want to stop at molecules. I want to go all the way down to atoms, because what is a molecule made of? It's made of individual atoms. Now, in this case, there's 2 hydrogens for every 1 oxygen. And so I can figure that one out. All right, so we're going to take our molecules. And that's molecules of water. And if I'm looking for hydrogen, I know that 1 molecule of water contains 2 atoms of hydrogen. And so basically it's 2 times that number, and 6.7. So basically this is a great big dimensional analysis problem going back between moles, molecular weight, atoms, and everything like that. Okay, so it's a great big conversion problem. All right, let's try another one and then we'll look at the lab. All right. Oh, you know what? We have that sodium chloride one there. Let's do that one. So the sodium chloride, if I have 10 grams of it, I have 0.171 moles of it. But I don't want to know that. I want to know how many. Okay, now in this case, this goes down to ions. So it's just a terminology difference. Okay, let's see, erase this bottom part. All right, so my 0.171 moles. I know that in every 1 mole of sodium chloride, there is 6.022 times 10 to the 23rd. Okay, now, and it's just a terminology thing. This would be formula units. Okay? And that answer is if you use the term molecule right there, that's absolutely fine. Technically, it's ionic, so it's not, but again, it's okay. 1.03 times 10 to the 23rd formula units of sodium chloride. Well, what if you want to get smaller? Well, let's go down to ions. So I have 1.03 times 10 to the 23rd sodium chlorides. And for every 1 sodium chloride, I know there's 1 ion of sodium. Or you could just write it like that. Or you could just write it like that. And it's a 1-to-1, so it happens to be the same for sodium and chloride. And all right. So that's how you get back and forth in between moles and mass. Okay, the only hard part is knowing where you're starting. Start big, go down to small. So if you're in grams, you have to get, oh, let me put that a little lower. Chemists only compare moles of things. We don't compare grams of things. We don't compare milliliters of things. We only compare moles. So if you're in grams, you need to get to moles. Once you're in moles, then you can go to the individual. Okay, so that could either be molecules if it's covalent, or it could be formula unit if it's ionic. Once you're into the individual unit, then you can go down to its pieces. And so molecules would go to atoms, and formula units would go to ions. And then I guess if you wanted to really, really go deeper, you could go all the way down to electrons, protons, so forth and so on. But moles is the key, okay? Moles is the connection. All right. Last thing I need to show you before we go on is mass percent. Now we could also do mole percent, but for instance, if we have carbon dioxide, carbon weighs 12.01 grams per mole, and oxygen each weighs 15.99 grams per mole. So together, its weight is 43.99 roughly. Okay, so that's its molecular weight. Okay, which is great, which is what we just did. But I'd really like to know what percentage is carbon and what percentage is oxygen. Now, this has nothing to do with chemistry. This is literally just math, percentages. The thing you're interested, divided by the total. And so carbon, there's 12.01 grams in the 43.99. Multiply by 100 to get to percent. And okay, 27, let me see, sig figs, I get 4. 27.30% of carbon. Now, I can either do the 15.99 times 2, so 31.98, divided by the 43.99. Or I could have subtracted this from 100 to get the oxygen. So 72.60, let me see, round up, 72.70. So in either case, okay, that's mass percent. You take the mass that you're interested in divided by the total mass. All right, last but not least, let me show you the lab. And where's it at? Right here. All right, so this is what you're going to print out. And again, it's just a visual. It's just a visual. So just from this little video, the molecular weight of a compound is calculated by adding up the blank of all the atoms. A mole of a substance contains blank number of particles. Now let's do a comparison. So a mole of lead will weigh, now right here, you're going to put greater, less, or the same as a mole of copper. And the units on a molar mass are blank. Okay, here's the lab though. Depending on if this is available, there is some in the drawer. I just don't know how much is there, but we're going to figure out how much sugar is in gum. So you're going to grab one of those pieces of chewing gum from the candy drawer, and you're going to weigh it with the wrapper. Okay, so you need to weigh it with the wrapper. And then you're going to chew it for about 5 minutes. Make sure you get all the sugar out. And then, as dry as it can be, I know that sounds silly, but as dry as it can be, with the wrapper again, take the final mass. And if you subtract those, that will tell you how many grams difference. And the grams that are different is actually the sugar. Now, granted, there's some flavoring in there, but we're going to assume it's all sugar. Ah, you can convert the grams you ate, okay, using the molecular weight of sugar into how many moles. And then you can convert that moles to molecules, and then you can literally determine how many hydrogen atoms you just ate from that piece of gum. Okay, another one that's kind of fun is, can you figure out the number of moles and molecule in your name? So if it's available, you can use chalk, you can use a crayon. Marker actually works, not quite as well as crayon and chalk, but you would weigh your crayon, you would write your name, and then you would take the weight of the crayon again. Okay, if it doesn't make a difference, okay, if the scale can't read it, write your name 2 times or 3 times or 4 times so that it can do a weight difference. All right, so you now have a mass of wax that was used to write your name. Here's the formula of wax, so you can convert that to moles, molecules. How many atoms of hydrogen of wax did you use? And then if some chalk is available, you can do the same thing with the chalk, which is calcium carbonate. All right. Here we're just going to look at some different compounds. So what is the mass, the volume, and the moles? How are they related? So you're going to weigh out 5 grams of each of these, and then any extra if Corey decides to give you some extras. So table sugar, which is sucrose, table salt, which is sodium chloride, some distilled water, and there's some iron shavings, some zinc shavings in the stock room. And then, there's some baking soda. So just some common household chemicals. You're going to weigh out 5 grams, as close as you can get to 5 grams. You're going to pour those into a graduated cylinder and just compare the volumes. Just because they have the same weights, do they have the same volumes? And then you're going to convert them into moles. So even though you have the same mass of each of those, do you have the same number of moles? And then determine the percent composition for each of those, not the iron and the zinc, but for any of the compounds. Not last. Next is the volume of a mole. This time, you're going to measure out 1 mole. Okay, so you can figure out how many grams that is. You're going to measure out as close as you can 1 mole of that and determine its volume. So it's kind of the flip side of the 1 above it. And then last but not least, with all of the density cubes, I actually have my mole sample. And so there should be in a container 1 mole of zinc. Okay, and uh, God, not a cylinder. It's not a square, whatever that is. It's a rectangular, whatever the volume for a rectangle is. Okay, there should be one for zinc, aluminum, copper, and iron. And if I'm remembering wrong, just write in the other two. But it should say on those pieces of metal 1 mole. Okay, so it's 1 mole of each of those metals. You're going to take the weight, and then you can use a ruler to figure out the length, the width, and the height, so you can figure out the volume. And you're going to see if those pieces of metal that I purchased that say they're 1 mole, if they're really 1 mole, because you can look at the periodic table and tell me how much it should weigh, and then you can see how much it does weigh. And then even better, you could actually divide it by the volume and you could look it up on the reference tables for the densities. Again, so not a hard lab. It's more of a visual, but it's just playing with the idea of what is a mole, what is a gram, how do you convert back and forth between them? Because the next one will be dealing with concentrations. All right, you might not be able to do all of those, or you could do all of those. Again, yes, I know it's like silly little labs, but it's the idea behind it that is the most important. All right, until next time, have fun and jolly out.